My name is Dr. Ping Ferlan. In this video, I will work out a few selected problems in the PowerPoint slides on the fundamentals of engineering biology review to help you with the exam preparation. As we stated in the lecture, the bacterial growth curve during the logarithm growth phase is modeled by the first-order kinetics described by equations 1 and 2, or by the logistic equation described in equations 3 and 4. In equations 1 and 2, R is the growth rate, mu the specific growth rate, X the cell number or concentration, which becomes X0 at initial time, and Xt at the growing time t. In equations 3 and 4, R is the growth rate, K the growth rate constant, X the cell number or concentration, which becomes X0 at initial time, Xt at the growing time t, and X infinity represents the maximum population or carrying capacity. Let's do the first two problems together using equations 1 and 2, and then the last one using equation 3. The first problem reads, what is the specific growth rate of an organismal growth batch culture that exhibits a constant change in cell concentration from 10 to the 3rd milligrams per liter to 10 to the 5th milligrams per liter during the 15-hour logarithm growth phase? So we see we're giving the initial concentration X0 here, 10 to the 3rd milligrams per liter, and concentration at time t, 10 to the 5th milligrams per liter, and also the growing time t, 15 hours. We're asked to find the specific growth rate, which is mu. We see equation 2 allows us to relate all these parameters together, which says the cell number or cell concentration at the time t is equal to the initial cell concentration times e to the specific growth rate mu times the growing time t. So we know everything but the constant mu. So we rearrange the equation to solve for it. First, we divide both sides by the initial concentration. Then we take the natural logarithm on both sides. So natural logarithm of the current cell concentration over the initial cell concentration equals the constant mu, specific growth rate, times the growing time. So we put all these known values in. Ln of the current cell concentration, 10 to the 5th milligrams per liter, over initial cell concentration of 10 to the 3rd milligrams per liter. That is equal to the specific growth rate mu times the growing time, 15 hours. Solve for mu, and mu comes out to be 0.3 per hour. The answer is C. The second question, during the exponential logarithm growth phase of a batch culture, the instantaneous value of the number of cells is 2000 and the cell growth rate is 300 per day. What is the specific growth rate? So here we see we're giving the cell number X, which is 2000, and the cell growth rate R, which is 300 per day. And we're asked to find again the specific growth rate, mu. Then we see equation 1 relates all these parameters together, which says the cell growth rate, R, is equal to the specific growth rate, mu, times the cell concentration, X. Put our known values in, 300 per day, and that is equal to mu times cell number, 2000 here, and solve for mu, which comes out to be 0.15 per day. Answer is A. Finally, the last one for a logistic growth batch growth model, the logistic growth rate constant is 0.8 per hour. If the initial concentration is 1.5 grams per liter and the carrying capacity is 2.5 grams per liter, the initial growth rate is most likely to be A, B, C, or D. Okay, so we see here we are given the growth rate constant K, 0.8 per hour. And the initial concentration, which is 1.5 grams per liter for the cells, and the carrying capacity, cell number at time of infinity, which is 2.5 grams per liter. And we're asked to find the initial rate R. So we see equation 3 relates all these parameters together, and that's the equation we'll be using. Initial rate is equal to the growth rate constant K times the initial concentration, cell concentration, times 1 minus the initial cell concentration over the cell concentration at the time of infinity. So we put all our values in. K is 0.8 per hour. Initial cell concentration is 1.5 grams per liter times 1 minus the initial cell concentration over the concentration at time of infinity, 2.5 grams per liter. So the answer is 0.48 grams per liter per hour. Answer is A again. As we said in the lecture, most questions in the topic of bioconversion are stoichiometry in nature. You wanted to relate the amounts through moles based on the balanced equations. If the balanced equations are given to you, that's great. Go ahead and use them properly. If not, you will need to use the equations in the handbook to figure out the coefficients. For instance, if we know the composition of an organic material is carbon 3, hydrogen 14, oxygen 2, nitrogen, which undergoes an anaerobic biodegradation, we can figure out the coefficients R, S, and M in the equation. Here A equals 3, B 14, C 2, and D 1. We can put these values into the R, S, M expressions and get the corresponding values of negative 0.75, 0.63, 2.38 respectively. The negative R value means that the water substance, instead of being placed on the left-hand side as the reactant, it is placed on the right-hand side as the product. See if you can use this balanced equation to solve for the first problem shown on this slide on your own. For the second problem here, it says aerobic biodegradation of glucose with ammonia is carried out in an experimental reactor. If the yield is 90%, the mass of cells with a composition of carbon, hydrogen 1.8, oxygen 0.5, nitrogen 0.2 produced per gram of glucose is mostly nearly A, B, C, or D. So we see here we're giving the grams of glucose, which is 1 gram. We're trying to figure out the mass of the cells, the actual mass of the cells, knowing the percent yield for the conversion is 90%. So from this balanced equation given to us, we can relate the mass of glucose to the theoretical yield or theoretical mass of the cells produced. Then we can use the percent yield to relate to the actual yield. Let's see how we figure out the theoretical yield. So we needed to go from grams to moles for our given. 1 gram of our glucose. Put it over 1 there. 2 moles of glucose. Using molar mass of the glucose to convert. 1 mole of our carbon 12, hydrogen 12, oxygen 6 has a mass of 180 grams. Carbon 6, hydrogen 12, oxygen 6. Then we relate the amount of 1 to amount of 2 through moles. In this equation, we get to see 1 mole of the glucose, carbon 6, hydrogen 12, oxygen 6, is able to produce 3.88 moles of the cells. Carbon, hydrogen 1.8, oxygen 0.5, and the nitrogen 0.2. Then relate the moles of the cells to grams of the cells. 1 mole of the cells with the composition of carbon, hydrogen 1.8, oxygen 0.5, and the nitrogen 0.2 have a mass of 24.6 grams. Carbon, hydrogen 1.8, oxygen 0.5, and the nitrogen 0.2. So we gain our theoretical yield of 0.53. Since our conversion efficiency is 90%, we multiply our theoretical yield by 90%, we get our actual yield, which is 0.48 grams. So the answer is D here. The last question on this slide is about unit conversions and knowing the meanings of the metric prefixes. Here, mega means 10 to the 6, kilo 10 to the 3rd, and milli 10 to the minus 3. Please give it a try and see if you can get it done correctly. As we mentioned in the lecture, the decrease of BOD, or biochemical oxygen demand, follows the first-order kinetics. In addition to equations 1 to 4, to be successful in solving problems relating to BOD, we also need to use the dilution equation shown in equation 5. It is also important to be clear if we are finding the BOD remaining L at time t, described by equation 2, or the BOD removal Y, or BOD at time t, described by equation 3. For instance, the 2-day BOD, or BOD2, means the BOD removal at day 2, not BOD remaining at day 2. The former is represented by Y2, or BOD2, and the latter, L2. Let's see if we could use the correct equations to solve the problems here. Here, a 15 milliliters unseeded domestic wastewater sample is mixed with 985 milliliters of distilled water. The initial dissolved oxygen level in the dilution is 8.2 milligrams per liter, and the level after 2 days is 6.2 milligrams per liter. The rate constant for biodegradation of the wastewater K is 0.10 per day. We wanted to find the ultimate BOD of the original sample. So we're giving the volume of the initial sample 15 milliliters. And the final volume of our dilution is 15 plus 985 milliliters. And this gives us 1,000 milliliters. The initial dissolved oxygen level, DO0, is 8.2 milligrams per liter. And the final dissolved oxygen level at day 2 is 6.2 milligrams per liter. And time t is 2 days. And the rate constant K is 0.10 per day. So what we could do is to find the ultimate BOD, or L sub 0, of the diluted solution. And from there, we then find the ultimate BOD of the original solution using the dilution equation. So first, we'll use equation 4 to calculate for the BOD removal at day 2, which is the dissolved oxygen at the beginning minus the dissolved oxygen at day 2. That is 8.2 minus 6.2 milligrams per liter, and that gives us 2.0 milligrams per liter. Then we will use equation 3 to relate BOD at day 2 to the ultimate BOD of the dilution, L sub 0. And that is equal to L sub 0 times 1 minus e to the minus kt. So we have 2.0 milligrams per liter for BOD at day 2. And that's the initial BOD or ultimate BOD. Multiply that by 1 minus e to the negative k 0.10 per day times 2 days. And from here, we can find the initial BOD or ultimate BOD of our dilution to be 11 milligrams per liter. Then we will use the dilution equation, equation 5, to find the initial BOD or ultimate BOD in the original sample. Okay, here, initial BOD in our dilution is the same as L sub F. So using equation 5, we'll find L sub I, which is equal to L sub F times V final over V initial. This gives us 11 milligrams per liter multiplied by the final volume over the initial volume, 15 milliliters. And this gives us the answer of 740 milligrams per liter. Chemical dose is an important concept in toxicology. You wanted to know if the daily chemical dose is safe or if it can generate an adverse effect. Chemical dose is defined as the mass of a chemical gets into the body in milligrams or micrograms divided by the total body weight in kilograms and the total exposed time in days. Let's do a chemical dose calculation here. A person consumes 2.0 liters per day of water. A chemical in the drinking water is at a concentration of 50 micrograms per liter. The person has a mass of 72 kilograms. Over a period of 30 days, what is most nearly the total dose of chemical the person consumes? Okay, so we're trying to find the chemical dose for this individual. We wanted to find the total chemical intake for this individual over the 30 days period. And that's going to be 2.0 liters per day of the water intake by the person times the concentration of the chemical in this water, 50 micrograms per liter, times 30 days. And this is the total chemical intake by this person over 30 days, which is then divided by the total body weight, 72 kilograms, and the total exposed time, 30 days. So we see the chemical dose for this individual is 1.4 micrograms per kilogram of the body weight per day. As stated in the lecture, when exposed to multiple toxins, you evaluate the hazard ratio HR for each exposure, which is the exposed dose over the reference dose, RFD, or the dose with no adverse effect, and then add all the ratios together. The total ratio must be less than 1 to be acceptable. The second question on this slide is about finding the HR for exposure to a single chemical, methanol. Let's see if the exposure dose is acceptable. Methanol has a chronic daily intake of 29 micrograms per kilogram of the body weight per day, and a reference dose of 500 micrograms per kilogram of the body weight per day. What is most nearly the hazard ratio of methanol? Here we are given the estimated exposure dose of 29 micrograms per kilogram of the body weight per day, and the reference dose of 500 micrograms per kilogram of the body weight per day. And our hazard ratio is the estimated exposure dose, 29 micrograms per kilogram of the body weight per day, over 500 micrograms per kilogram of the body weight per day. The ratio comes out to be 0.05A, which is less than 1. So this is an acceptable dose. The gas pollutant calculations involve the applications of ideal gas laws, where all temperatures must be in kelvins. Also a note on the ppm, or parts per million concentration unit. Usually, in aqueous solution calculations, ppm is a mass ratio. However, in gas calculations, you wanted to be aware ppm is by volume, or is the volume ratio of the pollutant gas to the mixture air. 1 ppm of the gas is 1 milliliter of the gas per cubic meter of the air, since 1 cubic meter equals 1,000 liters or 1 million milliliters. With that, let's see if we can solve the problem here. A concentration of 0.8 ppm carbon monoxide CO is measured in a landfill at a temperature of 25 degrees C and a pressure of 1.06 atms. The concentration of CO in milligrams per cubic meter of air is most nearly A, B, C, or D. Here we see our air is polluted by carbon monoxide, and the concentration of carbon monoxide is 0.8 ppm, which is equivalent to 0.8 milliliters of CO per cubic meter of the air. And we want to express that concentration in milligrams of the CO pollutant per cubic meter of the air. So we'll have to use PV equals nRT to convert the volume occupied by the CO gas to the mass of that CO gas at a given temperature and pressure conditions. So we assume that we have 1 cubic meter of the air. So the volume of the CO is 0.8 milliliters, or 0.8 times 10 to the minus 3 liters. The temperature of the CO is 25 degrees Celsius plus 273. That is 298 kelvins. And pressure here is giving to us 1.06 atm. And from there, we wanted to find the milligrams of CO. So PV equals the nRT. Out of the big force, we know everything but moles. So first thing is to find the moles of the CO in our gas sample, then convert that to milligrams of CO using the molar mass of CO to convert. So for CO, PV equals nRT. Moles of the gas N equals PV over RT. And we put our values in, 1.06 atm times the volume, 0.8 times 10 to the minus third liters, over the ideal gas constant R, 0.0826 liter atms per mole per Kelvin. Then multiply that by the Kelvin T, 298 Kelvin. And this gives us the moles of the gas to be 3.48 times 10 to the minus fifth. Then we convert that to grams, then to milligrams. Okay, 3.48 times 10 to the minus fifth moles of CO multiplied by the conversion factor. 1 mole of CO is equal to 28.01 grams of CO, the molar mass for CO. Then 1 gram of CO is 1,000 milligrams of the CO. With that, we get to see the answer to be 0.97 milligrams of CO in 1 cubic meter of the air. So the answer is A. You may wonder the difference between the threshold limit value, TLV, and the permissible exposure limit, PEL. Essentially, they are basically the same, except PELs are legal limits established by OSHA, while TLVs are recommendations. Let's see if we can answer the second part of the problem on this slide. An environmental engineer has been assigned to manage a laboratory. Table 1 shows the concentrations of possible toxicants the engineer found in the breathing zones at the 3 workstations. We wanted to decide if the concentration at station 2 exceeds the 8-hour TWA time weighted average dash TLV threshold limit value, as well as the 15-minute STEL short-term exposure limit. So let's first find the TWA, or time weighted average, for pentane at station 2. Using equation 1, the TWA equals the exposure during the first 2 hours, which is 700 ppm, times the time of exposure, 2 hours, plus the exposure during the following 4 hours, which is 410 ppm, times the time of exposure, 4 hours, plus the last exposure during the last 2 hours, 250 ppm, times the time of exposure, 2 hours, divided by the total exposure hours, which is 2 hours plus 4 hours plus another 2 hours. And this comes out to be 108 ppm. So for the 8 hour TWA TLV, equation 2 gives us the hazard ratio, which is the exposure 108 ppm over the recommended exposure of 600 ppm, which is equal to 0.18, that is less than 1. And for the 15-minute STEL, using equation 2, we can evaluate for HR, which is the peak value within 15 minutes, 800 ppm over the recommended value of 750 ppm, which is equal to 1.1, that is greater than 1. So the answer here is C. The concentration of pentane at station 2 exceeds the 15-minute STEL, but not the 8-hour TWA-TLV. Here, let's see if we could use the sun power level equations 1 and 2, to answer the first question on the slide. Two machines run simultaneously in a work environment. One machine has a measured sun pressure of 3 pascals and the other 12 pascals. The standard reference sun is 2 times 10 to the negative 5th pascals. What is most nearly the total sun level? A, B, C, or D? We are giving the first sun source with the sun pressure P1 of 3 pascals. And the second sun source with the sun pressure P2 of 12 pascals. And the standard reference sun with a pressure P0 of 2 times 10 to the negative 5th pascals. So we can use equation 2 to allow us to find the sun power level for each of the sun sources. Before we use equation 2, let's rewrite the sun power level in terms of the sun pressures. We can rewrite the sun power level L as 20 times the logarithm of the sun pressure P over the reference sun pressure P0. So the sun power level L1 is equal to 20 times the logarithm of its pressure, sun pressure 1, over the reference pressure P0, equals 20 times the logarithm of the sun pressure of 3 pascals over 2 times 10 to the minus 5th pascals. And this gives us a sun power level of 104 in decibels. We repeat the process for our second sun source its power level is equal to 20 times the logarithm of the pressure P2 over the reference pressure P0. It's equal to 20 times the logarithm of 12 pascals over the reference pressure, 2 times 10 to the negative fifth pascals. And this gives us the second sound power level of 116 decibels. So these were obtained using equation 2. Now we're using equation 1 to find the sound power level of these two combined sound sources. So L equals 10 times the logarithm of 10 to the L1. Here is 104 decibels over 10 plus 10 to the sound power level for our second source, 116 decibels over 10. Then we get 10 times the logarithm of 3.98 times 10 to the 11th for the first term, and 2.5 times 10 to the 10th power for the second term. So the sound power level for the two combined sound sources is 116 decibels, which gives the answer B. With that, I'm going to leave the last two questions for you to try, and we'll be very happy to answer any additional questions you may have during our scheduled sessions.